Hello everyone, I'm Simon with Sci Teaches, and this is going to be my video regarding node voltage, which I think is the most useful topic you will learn in your first circuits class. There's not a lot of prerequisite knowledge here. I'm glad to say that because my first two videos were a bit long. I don't want things to take 20 to 30 minutes to teach, because I know there are a lot of people. You guys can learn this faster than that. And it doesn't take, going to lecture 3 times a week to learn a topic for a quiz in 15 minutes. And I think that's a bit crazy, so I'm trying to do it faster and to the best of my ability. So here it goes. Node voltage, the only prerequisite knowledge you need to know is that for voltage, you should know from your physics classes, anything on E&M, is a potential, meaning it's a difference, okay? There's a difference between, if you have, and I usually say to ignore this, side of my screen over here, this right, but if you were to take the voltage is just a difference from this top point to the bottom point. So if I have some voltage plus minus V, that voltage is just here, the difference from here to here. So essentially, you can never measure a voltage just right here, okay? What you can do, though, is you measure a voltage there compared to another point, okay? So that's what node voltage seeks to do, is comparing 2 points. And essentially what that means is, if you want, you can set one of those voltages to whatever value you want. You could set it to 3, you could set it to 4 volts, you could set it to 5 volts, it doesn't matter. And what that will tell you, as long as you're consistent and you keep that node to be that voltage, the rest of the circuit will work out properly, okay? Now, what typically people do, though, is they choose a node and they set it to 0 volts, okay, or ground it. And that we will get into a little bit later. Okay, now node voltage. Just to teach the basics, here we have a simple 3-way meeting wire, okay? So we've got, as we see here, a current going through this, and a current going through this, okay? We've got 3 resistors, R1, R2, and R3, and we've got these 4 nodes, V1, V2, and V3, and V, okay? And V is what we care about. We're trying to find this voltage at point V. Now, or we could be finding the currents. It doesn't matter, okay? What we know about this already from previous topics is KCL. That is that I1 plus I2 plus I3 is equal to 0. They have to cancel out, meaning the outgoing voltage from here plus the one going out from here plus the one going out from here all have to equal 0, okay? And I actually drew this I3 the wrong way. I'm sorry about that. These all have to equal 0, okay? So let's take just one. Let's take I2. Is there a way that we can rewrite I2, which I have drawn here? And the short answer is yes, okay? We know from Ohm's law that V is equal to IR. So if I want to rewrite my I2, this current, I can say I2 is equal to the voltage across the wire over R2. And the voltage across the wire goes from, of course, the base of the arrow to the front. So it's the voltage drop, and I labeled these plus and minus here. That's VW, okay? So it's the voltage drop from here to here over the resistance, all right? And that gets us VW over R2. Well, we can also rewrite VW, because voltage is just a potential. It's a difference between these nodes, as V, the top node, minus V2, the bottom node, or I guess the left and right node, respectively. So when we rewrite, we end up with I2 is V minus V2 over R2, okay? And now if we were to do that for all the other nodes here, for this V1 and for V3, we would then be able to replace our KCL equation, I1 plus I2 plus I3 equals 0, with this squared equation beneath it, okay? And that is essentially what node voltage is. It's rewriting KCL, so you're using voltages and resistances. And I think the best way to go through this, as always, is let's get into an example. The first example, I'm just going to be going through the equations necessary to solve for some problem. And the reason I'm going to do that is because, as you can see on this diagram up here, in the center of the screen, I've got 3 nodes, and that can be a little annoying to solve 3 equations algebraically, so we're just going to find the necessary ones. Okay, so when you're looking at this problem, okay, it's asking you to find the voltage associated with the 20 ohm resistor right here, okay? And you may be a little confused to start. What should I be thinking? How do I go through this, okay? The first thing I notice is at the bottom here, I've got 5 nodes that are connected through nothing but components, okay? There's nothing but, there's no components in between any of these 5 nodes here. And what that means is they are the same. They are the same. There's no current flowing between them. There's no anything. They're the same. They have the same voltage, okay? And a way I can explain that is, well, let's take this wire here with this 20 ohm resistor. If I were to draw this wire here and connect it right here, is that any different? And get rid of this, of course. Is that any different? The answer is no, right? It's the exact same. And I could draw it anywhere. And in fact, some people, you go as far as to draw it directly connecting to that node, right? Essentially nullifying this entire wire, as well as replicating this wire here, okay? So, what I notice now is, well, I've got 5 nodes that are all the same, or technically 3, but some people like to count these out or 2, okay? So all of those are the same, so what I'm going to do is, because voltages are just differences, I'm going to, because of potential, I will set this common node, this node that has a lot of other nodes that are equal to it, I'm going to set that to 0 to make my life easier. And what essentially that's doing is grounding it. Some people will draw it as this little symbol attached to the edge, or some people will just like mark it as 0 volts. And I like to do that sometimes. It depends. I'll do both. So, what now? Now that I've set this equal to 0, and I recognized, okay, I wrote these in, this node is different from this node, is different from this third node. These 3 nodes are different, 1, 2, and 3, so I've marked them as such. So now I'm thinking, well, what do I need to solve? Well, V20 is this voltage drop here, which is the drop from V1 down to what? Down to 0, okay? So now all I need to find is V1. So can I first write an equation to find V1? When I recognize that V20 is equal to V1, I certainly can. We're using node voltage that we just learned. So I'm first going to say, I'm going to take this wire here, and I'm going to say, well, let's imagine these are all outgoing currents, right? And this current, this one right here, is V1 minus V2 over 5, okay? Because that's the voltage drop from V1 to V2 over its resistance. V over R equals I, okay? And that's going to give me this current, all right? Now, that plus, let's then take the current downwards, and that is V1 up here minus, all right, going down the wire, minus, what's down here? 0, so V1 minus 0, and then we're going to divide it by the resistance, which is 20. So that's going to be that outgoing current. And then what's the outgoing current in this other direction? Well, some people will mistake and go, okay, that's using my pattern recognition. That's V1 minus what's down here at this node or this node, 0 over Well, what resistance? Over infinity, right? Because resistors have, V1 minus 0 over infinity. Because current sources, power sources, have infinite resistance, right? And the answer is no. Okay, you're technically right that they have the infinite resistance, but what you need to worry about is, well, we're just talking about the current. They gave us a current flowing in this direction of 5I. So the only problem is it's flowing counter to the current we care about. So we'll just write that in as negative 5I. So we're adding right here plus negative 5 times I. All right. And then we're going to go ahead and we look at this equation, and I know that I have to find V1, but now my V1's in terms of V2. So let's try and write an equation for V2. And we do the same exact thing. Let's start from the left, I guess, this current, V2 minus V1 over 5. Then let's do this downward current. That's V2 minus 0 over 40. Then we'll do the right current. That's V2 minus V3 over 10. Right? Pretty simple. And then the same exact thing for V3. We look at the left one, and that is V3 minus V2 over 10. Then we look at this downward wire. And what we notice with this downward wire is, well, there are two components. There's a power source, isn't there? So how exactly am I supposed to deal with that when doing node voltage? There's a little trick I like to do, and I can kind of show that in the next example, but because we've already marked this as 0, why can't I just make another node and mark that second node as 11I in and of itself? And you can, and that's what I like to do. So we're going to say that's now V3 minus 11I, and over that resistance, which is 5. And then for this right wire, we're going to do the same thing. We have this as 0. We can just make another node and say this is 96, right? Because this plus minus, right, is just a voltage difference. It's just a potential. So we now have V3 minus 96 over 4. And the only thing now that we need, the only other component we need to solve this problem, to find our V1 and our resulting voltage associated with the 20 ohm resistor, is I. I we have not found. Okay, so let's put I in terms of some known quantity. And how can we do that? Well, we see that I is marked in our equation as the current drawn going from the second voltage, V2, to ground across the 40 ohm resistor, which is just, of course, V2 minus 0 over 40. So we can write that in. And those are all 4 equations you need to solve this problem. And what I would do from here, if you're asked to, although you probably won't be when doing homework or whatever, or even quizzes, is I would substitute in I into my equations, and then I would run a matrix on my calculator or something like that, instead of trying to go through solving it on my own. Just because that can take some time. All right, this second example, I'm going to show you how I do these problems really, really fast. I'll show you my thought process. This is a simpler example, but it will allow me to get my point across a lot easier. So let's go through that. In this example, we want to find the power associated with this V over 2 power source. So how are we going to do that? Well, what is V over 2? It's marked here. V is the voltage drop from this 9-volt source to V1, which I've marked for us, to this node here, over this 20 ohm resistor. And immediately what I noticed again is common node, one common node between these 3 points. So I just grounded that. You could also, by the way, ground right here. There's nothing wrong with that. I just decided to do it at the bottom because, I mean, It just looked easier to me, but it's essentially the same. So what I do is, my little trick is I will erase all these voltage sources. If I have a voltage source, I'll erase it, or a current source. I'll just get rid of it and say, oh, that has infinite resistance. There's nothing there. Trash that. And instead, I'll mark it somewhere else. So I marked this as having a 9-volt input, okay? Instead of like having my connected 9-volt source. And you may be asking like, oh, well, why the hell would you do that? That's kind of stupid. It just gives me a clearer mental picture, okay? And if you look down here with this dependent voltage source, I've done the exact same thing. I've erased the connection to ground, and I've marked itself as a V/2 input. And then down here, there's nothing you can really do. This just has a 0-volt input, so I went ahead and marked it as such. And the reason I do this, as I was trying to get into, is this circuit on the right-hand side of my screen looks a whole hell of a lot easier to analyze than this left side circuit. It just does. Maybe it doesn't for you. I just found that it does for me, because I'm now dealing with just 3 wires instead of like 5 different connections, right? So we know we have to find V, and by association V1. So let's just run our node voltage. Why not? So using this left-hand side, if we imagine some current to the left, right, left, downwards, right, going out, it's V1 on this left side, V1 minus 9 over 20 right here, then V1 minus V2 over 10 going down, and then V1 minus 0 over 40 to the right. All right, and then, well, I now have V1 and V/2 directly related, or V1 and V somehow directly related. I need to find V/2 though. Well, is there some other way I can directly relate them? Because if I can get 2 unique relations between 2 unknown variables, they are solved, right? That will always be the case. So here I notice that, well, V right here is just the voltage difference from this 9-volt minus this V1, right? It's just a voltage difference from 2 nodes. That's just a simple subtraction. So V is equal to 9 minus V1, and I've rewritten that as V1 equals 9 minus V. And the reason I did that is so when I plug this, substitute this into my top equation, I don't have to find V1 first, because V is more important to me. Because I need to find V/2, right? Sorry. So I went ahead and plugged that in. I did substitution, and I'm not going to walk you guys through that whole process. You should be able to do that on your own. I found V is equal to 5 volts. V1 is equal to 4 volts. Now, to find power associated with this 5/2 voltage source, okay? Because 5, right, being V/2 is the source. That's 5/2, right? So 5/2 source is, I just need to find current, okay? Particularly the current flowing into the positive end of my source, right? So I went ahead and I grabbed this bit here, this wire, and I went ahead and drew it down here for you guys. And you'll note this current is using node voltage again, right? This current is 4 minus 5/2, and that's a voltage. That's the voltage difference. Now we have to divide it by resistance, 10, to get current, okay? So we went ahead and wrote that here. 4 minus 5/2 divided by 10 is equal to current, and that is 3/20 amps. So now power is positive V times I when we're flowing through the positive terminal. So we have 5/2 voltage times current, 3/20, and that gets us a power of 0.375 watts, and that is your answer. Thank you very much.